program. The last lecture on the LHC series from Professor Xu.
You hear me well? Yes? Okay. So, I will continue the why. Oh, okay. Hold on. Give me a second. This controller doesn't work. It's okay. I can just use my computer. Right. So I plan to cover 3 topics today. I'll finish the Standard Model discussion, including the Higgs, and then I'll talk about beyond Standard Model physics. Then I'll talk about the physics beyond the LHC. The Standard Model, we continued the discussion yesterday. There are several electroweak effects. For example, there are 3 basic Standard Model parameters. We can do an over measurement on that, but based on these 3 parameters, you can actually derive the other electroweak parameter. So if we measure all of them, then we can do an over-constrained fitting to compare if all the measurement is consistent with the model predictions. So will that be exactly consistent? Then that's one way that we can try to probe new physics beyond the Standard Model. So in terms of WZ, Large Hadron Collider basically we discover all these Standard Model particles in a very short time. So we actually use W boson, Z boson because they are a lot and also they are quite clean signature. They are also called standard candle in Large Hadron Collider. We use that to calibrate all our basic objects. So, for example, we measure the WZ cross section, and here, one thing interesting in Large Hadron Collider is that if you look at the charge W, positive charge W and negative charge W production, and you could see that charge W, positive W is higher, and it's because in the proton collider, you still have a more valence quark than the C quark interaction to produce a negative W. So amazingly, like when we just turn on the machine, measure our cross section, and compare to the theory prediction, it's just right on. This gives us quite confidence on the Monte Carlo generator we used, and also all the theory calculation we used can predict the known background, and this gives us a solid foundation to establish a new physics discovery, including the Higgs. So there's a particular feature for the W mass or top mass. So it's known that if you calculate the radiative correction of a W mass, and you could introduce the top bottom quark loop and also the Higgs loop, and this will introduce a way to associate the 3 important parameters in the Standard Model: the W mass, top mass, and Higgs mass. So before we discover Higgs, we can actually use the top mass and W mass, try to predict what's the range, the possibility for the Higgs mass. And actually beyond the top mass and the W mass, there are all kinds of various electroweak parameters. When you try to consider the correction for those parameter calculation, then you can associate the Higgs mass to all of them. Okay, thank you. So, okay, now this. So in this plot, for example, the solid black dot is the direct measurement for each parameter. And if you look at the blue is the one that you use indirect determination. That is, you just take this parameter out from the electroweak parameter determination formula, and then you use the other parameter to predict what this variable will be. And then you can also try to include the parameter into the global fitting. Then you could see that actually for some parameter, the indirect determination or the fit result have 2 sigma fluctuation from the compared to the direct measurement. Yeah. So there were some analyses actually quite interesting. Try to put all the measurement which have more than 1 sigma deviation into one group, and for the other parameter which have within 1 sigma agreement with the parameter into another group. And when you do that, you might be able to do some theoretical argument or try to find some pattern why some of the group have a larger deviation from the other. But in general, if you look at consider all the parameters altogether and apply the statistics theory, and this kind of fluctuation is considered to be in agreement with the certain model. So in the right-hand side plot is the fit result that you try to include the new Higgs mass measurement or non-Higgs measurement. Okay. So in general, like even the largest deviation from the direct measurement is still only 2.5 sigma. So it's a number that might possibly happen, but not really put some tension here, like there might be new discovery. So if we continue the standard model procedure measurement, let's focus on W mass. So this is the fit result, including the Higgs mass or no Higgs mass, and then compared to the direct measurement of W mass. So you could see that the fit prediction and the central value of the W mass measurement is about 1.5 sigma. The value is 1.5 sigma higher than the fit. And for the top, we have actually one latest development. It just happened in February. That is, we established a combined fit result of Tevatron top mass measurement and LHC measurement. It's the first time ever trying to combine them together, and we get the most precise top measurement right now. And if you compare this measurement to the fit with or without the Higgs, it's also about 1.5 sigma. Essentially, it's a 1.5 sigma lower. The measurement lower than the fit result. And in terms of Higgs mass, so Higgs is discovered mainly through the 2 photon and the ZZ final state. And these 2 channels give you the best estimate of the Higgs mass. Although we also try to include the channel, for example, WW, together trying to estimate what the possible extent will be, but it actually will not contribute too much because of the strong constraint from the two channel. So if we combine the measurement of the Higgs mass from two photon and the four lepton channel, then we can get this combined information about the Higgs mass will be. And the latest result, you can see here, the Atlas and CMS start converging. Yeah. So I still remember right after the Higgs discovery announcement, 2012, the two experiments still have some relatively larger discrepancy in terms of mass measurement is about 1 GeV. But now, as time moves on, we improve our understanding of the detector and update our analysis. The Higgs mass now kind of converges to 195.5 GeV range. So now we can put all the three measurements together. So this is plot shows you the W mass versus top mass relation, and this contour is the measurement result of the two without including the Higgs. So the Higgs is represented as a band over here, and so now this is the overall region that all the three mass measurement could have coexist without contradiction to the set model. So here you could see now the critical thing is actually how we can further improve the W mass. Yeah. So if we can further improve W mass, then this air contour will become smaller. And if our central value in the end actually have more than 5 sigma deviation from what predicted Higgs is, major Higgs is, then there will be an indication of the new physics. Yeah. So in terms of W mass, actually currently the only experiment which can further push the W mass precision is Large Hadron Collider. So there's actually another final round of the W mass measure from Tevatron, both from DCL and CDF. Once they finish, then there will be expected another 10% improvement of W mass measurement from Tevatron. But after that, LHC is the only machine which can produce a large number of W to push the frontier of the W mass measurement. It's a relatively difficult analysis in LHC because we have a pile up, and this will really put a lot of challenge how to understand the lepton energy spectrum in order to measure the W mass. So probably to really give a real understanding or get the best understanding of or to probe the new physics using the W mass measurement, we will really need a eParsimon machine which can non-ambiguity measure this quantity to a very high precision. Right? So let's move on. And now we talk about the Higgs mass. Yeah, and we want to understand further if that's a real Higgs. So we start asking what's the quantum number for this new particle. And the way to do that is we have a channel Higgs2ZZ which further decay to lepton. So we can use the angular information of the decay product, and we can construct the kinematic likelihood ratio, which is you can put different quantum number of the hypothetical particles, and then compared to the CP even spin zero, like this is the certain model Higgs quantum number. So we can construct this discriminator and to see if the new particle hypothesis is more preferred than the scalar Higgs hypothesis. And just we can use this way to construct the statistical number to define its significance. So here, this is CLS technique. So I will not try to explain what it is, but I will try to comment that here just shows you how significant this is unlikely to be the new particle. Okay, so you can see that if you put some simulation that the model you try to probe is actually the scalar Higgs, then the expectation, which is the blue here, is close to a 3 sigma. So this is unlikely to be the new particle. And in terms of if you put the spin zero assumption here, then this significance is lower. Then it's more preferred to be a scalar Higgs. And then you look at the real data result, the break. The break follow the expectation quite well. The general picture is that the data prefer to be with lower significance. That is, it's more likely to be the scalar, a scalar, yeah, compared to the other quantum number assumptions. Okay, so but just it's become customized internal agreement. Like we want to claim a measurement until we achieve the 5 sigma. So if you look at this expectation to reach the 5 sigma exclusion of the hypothesis, we still have a long way to go. So we now can say that this new particle is more likely to be or prefer to be a scalar particle. Then how about the other quantity? So to observe this particle, we have a theory how it is produced. It has 4 major production channels. Actually, the Coulomb fusion is the dominant production channel. And we also have prediction about how this particle can decay. And the decay branch ratio that actually controlled by the coupling between the Higgs and its daughter particles. So we also have a prediction about what its decay width will be. So now we know that the Higgs is about 125.5 GeV. So you can see that the decay width is very small. It's in the MeV level. Yeah. So it's compared to the 125 GeV, the Higgs particle just looks like a really narrow resonance particle. And the other interesting feature is that if this Higgs is not light, if it's able to be heavy, yeah. So after it beyond the two gauge boson mass, then you can see that it starts getting the really larger weight. So if the Higgs is actually a 1 TeV mass particle, the decay width is equivalent to its mass. So at that time, you probably will not call it the resonance. Yeah. So anyway, let's go back to our current observation. It's a very small width, so it has a very small coupling. How can we use the current data to explore and compare to the theory? So let's look at the Higgs to ZZ to 4 lepton as an example, how we do it. So this is a 4 lepton invariance plot. You could see that there is a Z boson decay to 4 lepton background, and there's a continued background here, and then you have a 2 unshelled Z production here. Okay? And now you see certain amount of Higgs show up. So the height or the axis of this peak, you can use that to determine what's the decay rate times the production rate. And then you can use this to examine if you have a new physics. Yeah. So to do this well, actually, we need an advanced theory calculation to really give us a high accuracy calculation with a small uncertainty. So we even go to the next level of the calculation. Yeah. And also, we need to understand the background. Yeah, this blue component to very well. And we use the most advanced generator up to density order. And then we also need to have good control on the Poisson distribution function. So to really understand if you have a coupling which match to the expected theory, you need good control on all these factors. So this is an innovation about how we actually accumulate the data for the Higgs when you have a small data up to what we have now. This is a nice scenario. So everyone have a training largest collider. Hopefully, with the surplus somewhere here, in the future we have something grow up here, so we can find something particle. So in order to extract information about coupling, so what we do is that we define a quantity called the signal strength, mu. So the mu is defined as is the predicted production cross section times branch ratio, and the fiducial acceptance and the particle efficiency times the integrated luminosity. And you sum up all the channels. Yeah. Then you have the expected yield. Okay. And now you can compare this expected yield to the observed data. And this mu just determines the fraction of the difference from the expectation. So for mu equal 1, that means your observed data number yield is consistent with the prediction. Okay. So then we know that the P, this is a production channel. We have various production channel. We want to start each one of them. And in terms of the decay channel, we have 5 active channel analyzed right now. And if now you see this 4 times 5, there are 20 channels. If one of the channel have a large deviation from certain amount of prediction, then we say there's a new physics. Okay. So the criteria is very simple. You just need one have a deviation. So you can do further, more detail. Instead of sum up each channel, then define mu strengths for each of the decay channel. So you could further break down the production times the decay channel included together. Okay. So then you have a more detailed the signal strength, not just the sum of all the production channel, but you try to separate two. So here you can further define signal strength based on the decay product. So you can define the subcomponent of the branch ratio. So this is the result of the signal strength. Here is the result for the atlas, and you have a combined strength, signal strength here. So the combined result is 30% higher than the molecular prediction, but you can also see that this is about 1.5 sigma upward fluctuation. Yeah. And in terms of the CMS is a downward fluctuation. So if you combine both atlas and CMS, oh yeah, so actually it's right on. So the combined atlas and CMS result conclude that the signal strength of Higgs production actually consistent very well with Standard Model. So the other thing I want to point out is that you could see there are two channels with really high uncertainty. These two channels that so far we did not have direct observation of the Higgs yet. So these two channels still give us some window that there may be something new. So they are the tau channel and the Ula channel. Okay, but you might follow that tau now. If you just count the significance, it's now actually have a more than 3 sigma significance to be behave like a Standard Model Higgs. And these two channels will have to be one of the most important channels. We want to get the early result out when we start the run in 2015. So the signal strength is defined in an easy way that you just compare the ratio of the prediction to the observed yield. But if you want to further do a discussion about do I have a correct measurement? Sorry, not correct measurement. Do I have an agreed measurement of coupling strength compared to the prediction? So we can use this the effective Lagrangian. For each coupling vertex, you can introduce a constant, and our job right now is that how can we extract this constant value, and then if this value constitutes 1, then it means that it's considered a model. So this parameter was you write down, and then in particular the top here, the top coupling here actually contribute to the production. Yeah, because the way we produce the Higgs actually is a gluon with top loop. So you have a top coupling to the Higgs, then give you the Higgs. So you can imagine that if you compare to the signal strength we showed earlier, because signal strength give you both production and the decay, then you can actually derive some connection between the signal strength and the coupling strength here. Take one example. When you have a Higgs decay to WW, then you can define the W coupling and the Higgs coupling strength. Okay, and here will give you the relation of the signal strength of WW. But because you try to divide by total decay yield, so you get the signal strength of the branch ratio. So then, if you look at this is one example of the VBF production. So you have a quark emit the gauge boson and then fuse to a Higgs. So at this vertex, you can define the signal strength of the VBF production. And this is if you look at the coupling parameter in the previous Lagrangian, and you will see that it has a contribution not just coming from the WW chain, you also have a contribution from the Z. Okay? So then in the end, if you want to define what's the VBF production Higgs, which further decay to WW, this the signal strength will be the product of the two. Okay? So now you eventually, once you make the product of the two, you basically derive from this signal strength to all the coupling parameter. Okay? We define from the effective Lagrangian. So basically, we accomplish one task, which is you can derive all the correlation between the coupling constant and the signal strength you derived earlier. So this is the result of the coupling strength from the most inclusive data set from CMS. And if you look at the solid dot, this is the